Good day, everyone. And I hope you guys have been successful working with your slope fields that we introduced on Monday. I've already gotten some submissions of those. They looked pretty good. I just hope you're continuing to work on that. And you might have noticed that some of those differential equations or derivatives involved more than just x. They involved x and y. Maybe you were wondering, when would we ever see a derivative that involve both x and y, such as, you were graphing with your slope field. One of the problems on your slope field might have looked like this, that the derivative of y with respect to x involved both x and y, maybe something like this. And maybe you were wondering, when have we ever seen a derivative of a function y that involved both x and y squared? Well, you actually have seen that before. Let me just remind you of that. It was probably when we were working with this topic of implicit differentiation, equations that might not necessarily be able to be solved as a single function like this one is, but I can still represent the slope of the equation, or the slope of the graph, dy dx. And here's an example of that. It's asking us to implicitly differentiate this equation. Now, I encourage you to pause the video right here and maybe take a look at this. Do you remember how we did this? This would have been back in the fall semester toward the end of the differentiation chapter. I encourage you to pause the video right now and take a look at this and see if you remember how that worked. Okay, well, let's work through this one anyway. Now remember, you're differentiating with respect to x. Remember, so the idea here is that it is implied that y stands for a function of x. That way, when I get to the second part, the derivative of y squared, you're really thinking of it as a function squared, and you're going to have to use the chain rule. So the first part is 2 times the function to the first power, but then you have to differentiate the inner part. I'm going to try and make the difference between y to the first power and y prime. And then the derivative of the constant 100 would be 0. Now, remember, what we're trying to solve for is the y prime, or dy dx. So if I were to add this negative term entirely over to the other side, I get 2x equals 2y, y prime. And if I want to solve for y prime, we're just going to have to divide by 2y. And of course, the 2's would just cancel out. So my derivative is x over y. Or we could write that dy dx equals x over y. Okay, so there's right there an example of a derivative that is expressed with two variables, x and y. So I'd like to take this exact one now and try and show you how we would reverse or undo this process back to an equation like x squared minus y squared equals, if at least, if not 100, at least a constant. X squared minus y squared equals a constant. And so that's what I've got on the next screen here. And this is the purpose of this, is to demonstrate the whole process of what we call solving a separable differential equation. And so the process we use is called separation of variables. Okay, but this is just a good example of what we call a separable differential equation. One very important thing to start with is that your derivative notation should always start off with dy dx instead of like y prime or f prime. Let's always use dy over dx equals x over y. Now, this notation over here is not really a separate numerator and denominator, dy and dx, but for the purposes of this, we're going to treat it like it is. So I can now, my goal in the next step is to separate the four components of this equation so that everything involving y and dy appear on one side of the equation, and everything involving x's and dx's appear on the other side. So for example, I'm going to treat dy and dx as separate quantities. So I can do things like multiply both sides by differential dx. and bring dx over to this side. And I can also multiply both sides by y to remove it here and bring it over to this side. So let's just clean this up a little bit. The right side now has x multiplied by dx, and the left side now has y multiplying by dy. And at this stage right here, we say that the variables are separated. That's a very important first stage, is to have all the y's and dy's separated from all the x's and dx's. Now, what each side looks like is basically looks like an expression that normally appears in an integral, and that's what we want to do next, is to reverse these differentials by integrating. So if these two sides are equal, we should be able to find the antiderivative of each side and say that they are equal. So now each of these sides of the equal sign is an integral with respect to its own variable. This is an integral with respect to y. Pretty easy one. This is virtually the same integral, but with respect to x. Okay, so they both will integrate with the power rule. And so the integral of y would be 1/2 y squared plus a constant. And on the other side, the integral of x would be similarly 1/2 x squared plus its own constant. Now, I actually sometimes will just use subscripts here for now. So maybe I'll call that one constant 1 and constant 2. And I think the next step is let's just combine the constants. You'll do this every time. In fact, I'll talk about a pretty shortened way to do this in a minute. But if I want just to subtract one constant from one side and bring it over to the other side, it now is 1/2 y squared equals 1/2 x squared. And then this entire thing is a constant, really. I'm just going to parenthesize it. Right? And in fact, what almost everyone does is just, if you're combining the two constants together, let's just forget about calling it C2 minus C1, and let's just call it one big constant C, right? So starting again at the top, I've got 1/2 y squared equals 1/2 x squared plus a constant. Now I'd like to just, you could leave it like this really, but let's just multiply out by 2 to get rid of the fractions here. So let's just double everything. And we're going to do another little thing with the constant now. Since we don't really know what this unknown constant is, to double it and call it 2c really isn't necessary. Anytime I do anything with the constant, we're just going to keep renaming it c. So I've got y squared equals x squared plus c. And actually, we could get it to look like the previous example that we differentiated by just getting the y's and x's on the same side. So this now becomes y squared minus x squared equals c, which is virtually the same equation we had in the previous slide, except in that one, the constant was given to be 100. Okay, so we had y squared minus x squared equals 100 there. Okay, virtually the same equation though. So that gives you an idea of how the separation of variables works. So let's take a look at our list of directions here. And in our example, first thing we did was we made sure that we used the notation dy dx for any derivative of y. And so if the equation contains the symbol y prime, I want you to change it to dy over dx. Second, you perform algebraic operations to both sides until you have all the terms involving y and dy on the one side and everything involving x and dx on the other side. This is often the part that depending on the complexity of the problem, this can be either really easy or sometimes it can be a little tricky. It's important that you simplify as best you can in step 2 as well, because remember the next step is to integrate, and so you want to make sure that the separated sides are in the form that you would know how to integrate them. 3, integrate both sides with respect to the corresponding variable. So the side that has y, you're integrating with respect to y. The side that contains x, integrating with respect to x. Now, you saw me put a plus c1 equal, and then on one side and a plus c2 on the other side. From now on, we're just going to instead of doing that and then combining them, we're going to include the integration constant only on one side of the equal sign. You'll see us do that in the next example. 4, solve for y if possible, otherwise arrange pretty much as you wish. So you saw in the last example, we just kind of left the equation y squared minus x squared equals c. That's sometimes is perfectly fine and appropriate to do that, as opposed to writing it y squared equals x squared plus c. And now you really can't write it solve for y without doing things like plus and minus x squared plus c, which is a little bit ambiguous yet, because really your goal is to get it down to a single function. So unless there's more information given, usually sometimes we often leave it this form here or this one. Okay. We're going to stop this video right here, and then in the next video we will have a number of examples about solving differential equations in this way.